right now, at this very moment, hundreds of billions of stars are burning in the sky above you. That seems normal. It seems like the default state of things, the backdrop against which human history has always played out, the permanent ceiling of our world. But it isn't permanent. It isn't even close to permanent. What you see when you look up at the night sky is a temporary arrangement, a brief, improbable, luminous accident, and we are living inside it. Before this moment in cosmic history, the universe had no stars at all. It was dark, formless, and silent in a way that our minds can barely conceive. And after our current era, after what astronomers call the Stelliferous Age, the age of stars, the lights will gradually go out, one by one, over timescales so vast they have no name in ordinary language. What surrounds us tonight is not the eternal face of the cosmos. It is a phase, a season, a window that opened billions of years ago and will close again long after the last creature capable of noticing has ceased to exist. We were born into the most luminous chapter of a very long, mostly dark story, and almost no one stops to think about that. Almost no one looks up and feels the full weight of the coincidence that out of all the possible moments to exist, across a timeline that stretches from the first quantum fluctuations of creation to the cold silence of maximum entropy, trillions of years from now, we happen to be here during the brief, bright interval when the universe is alive with stars and galaxies, and the warmth necessary for complexity, when the raw ingredients of curiosity and consciousness can exist at all. To understand how extraordinary that is, to really feel it rather than just acknowledge it as an interesting fact, we have to go back, far back, back to a time before light had any place to land, before matter had organized itself into anything recognizable, before the universe had done anything at all except expand and cool and wait. The universe began approximately 13.8 billion years ago in an event we call the Big Bang. But that name is misleading. There was no explosion in the conventional sense, no sound, no shockwave, no debris flying outward through a pre-existing void. There was no void to explode into. Space itself came into existence in that initial moment, along with time, energy, and the fundamental laws of physics that would govern everything to follow. In the first fractions of a second, fractions so small they dwarf our most precise instruments, the temperature of the universe exceeded a quadrillion degrees. The entire cosmos was smaller than an atom, and then smaller than a grain of sand, and then the size of a grapefruit. And it was expanding at a rate that staggers the imagination. Within the first 3 minutes, protons and neutrons were combining to form the nuclei of the lightest elements: hydrogen, helium, tiny traces of lithium. That was it. That was the entire periodic table of the early universe. 3 elements, in roughly a 3-to-1 ratio of hydrogen to helium, scattered across an expanding ocean of energy and radiation. No carbon, no oxygen, no iron, no silicon, no phosphorus, no nitrogen. None of the elements that make biology possible, that make chemistry interesting, that make the material world as we experience it so varied and complex. The early universe was chemically monotonous in a way that would have made it forever sterile if something hadn't changed. For the first 380,000 years, even those simple atomic nuclei couldn't hold on to electrons. The universe was too hot, so hot that any electron captured by a nucleus was immediately knocked away by collisions with high-energy photons. The cosmos was, in effect, an opaque plasma, a fog so dense that light could not travel through it at all. It was bright in the sense that energy was everywhere, but it was not transparent. You could not have seen anything, because photons were constantly scattering off free electrons, unable to travel in a straight line for more than a tiny fraction of a second. And then, 380,000 years after the Big Bang, the universe cooled enough for electrons to finally settle into stable orbits around atomic nuclei, in an event cosmologists call recombination, though it was the first time, not a reoccurrence. Neutral atoms formed throughout the universe all at once. The fog lifted. Light was suddenly free to travel. The photons that had been trapped in that plasma streamed outward in every direction, and the universe became transparent for the first time. Those photons are still traveling today. We can detect them, a faint microwave glow that fills the entire sky uniformly, a remnant heat signature from that ancient moment of liberation. We call it the cosmic microwave background, and it is the oldest light in the universe. When we map it, we are looking at a photograph of the cosmos when it was 380,000 years old. We are seeing the moment the universe first became visible, and it is almost perfectly smooth, almost perfectly uniform, with only the tiniest variations in temperature that would eventually, over billions of years, grow into everything we see today. This is the part of the story that rarely gets told. After the initial fireworks of the Big Bang, after the fog cleared and light was free to travel, there was nothing for that light to come from. The universe was filled with neutral hydrogen and helium gas, slowly cooling, slowly drifting, pulled here and there by gravity toward regions of slightly higher density. But there were no stars yet, no galaxies, no sources of light of any kind. For hundreds of millions of years, some estimates suggest as many as 500 million years, the universe existed in a state of total darkness. Not the darkness of a room with the lights off, not the darkness of a moonless night, the absolute darkness of a cosmos that had not yet learned how to shine. But after recombination, the universe went dark again. Cosmologists call this period the Cosmic Dark Ages, and it lasted longer than the current age of our solar system. It was a patient, silent, featureless time. But beneath the surface, in the invisible architecture of density, fluctuations left over from the Big Bang, gravity was doing its slow, relentless work. Regions that were even slightly denser than average were pulling in surrounding gas, accumulating mass, growing denser still. The process was glacially slow by human standards. But on cosmological timescales, it was inexorable. And then, somewhere between 200 and 400 million years after the Big Bang, though we are still refining this estimate, the first stars ignited. The first light since the Big Bang itself appeared in the universe, not from a single point, but from countless locations scattered across the cosmic web, wherever the gas had grown dense enough to collapse under its own gravity and trigger nuclear fusion at its core. These first stars, which astronomers classify as population 3 stars, were profoundly alien compared to anything that exists in the universe today. There is no way to observe them directly. They formed and died before the Milky Way existed, and their light, after traveling for more than 13 billion years, has been stretched by the expansion of the universe far beyond the visible spectrum. But we can infer their properties from theory. And what theory tells us is remarkable. They were enormous, potentially hundreds of times more massive than our Sun, some of them possibly approaching the theoretical upper limit of stellar mass, beyond which radiation pressure would tear them apart before they could fully form. They burned at temperatures that made them shine blue-white, with an intensity that dwarfed anything in the modern universe. And because they were so massive, they burned fast. Where our Sun will live for roughly 10 billion years, these first stars may have lived for only a few million, barely a cosmic eye blink. But in dying, they did something that would change the universe forever. When a massive star exhausts its fuel, its core collapses catastrophically and then rebounds in a supernova explosion, one of the most energetic events in the known universe, briefly outshining an entire galaxy of hundreds of billions of stars. In the process, the intense heat and pressure of the explosion forge heavy elements through rapid nuclear reactions and scatter them across vast regions of space. The first supernovae seeded the universe with carbon, oxygen, neon, magnesium, silicon, sulfur, iron, elements that had never existed before, produced in the nuclear furnaces of those first brief stars, and then flung outward to enrich the surrounding gas clouds. This is not a metaphor. This is literally what happened. The carbon atoms in your body, the oxygen you are breathing right now, the iron that carries oxygen through your blood, none of it existed in the early universe. It was made in stars. It was scattered by explosions. It drifted through space for billions of years, was incorporated into new clouds, collapsed into new stars, exploded again, was scattered again, slowly building up a richer and richer chemical inventory across the cosmos. By the time our solar system formed 4.6 billion years ago, the local region of the Milky Way had been enriched by multiple generations of stellar death. The raw material available to build planets, to build us, was incomparably richer than what was available at the beginning. You are not visiting the cosmos. You are built from it. You are what the universe does after it has had enough time to practice. The several billion years following those first stars constitute what cosmologists sometimes call the cosmic renaissance, a period of increasingly rapid and complex activity. Galaxies were assembling, drawing together not just ordinary matter, but vast halos of dark matter, whose gravity provided the scaffolding for structure to form. Stars were being born at an accelerating rate, and their collective light was reionizing the neutral hydrogen gas that filled the space between galaxies, making the universe transparent on large scales in a second great transformation after recombination. The cosmic web, the vast network of filaments and voids and galaxy clusters that defines the large-scale structure of the universe, was taking shape, driven by the invisible hand of gravity working on the initial density fluctuations from the Big Bang. Star formation reached its peak roughly 10 billion years ago, about 3.8 billion years after the Big Bang. At that time, Galaxies were forming new stars at a rate perhaps 10 times higher than today. The universe was denser, hotter, more active, more chaotic. Galaxies were colliding and merging with greater frequency, triggering enormous bursts of star formation in the resulting chaos. Quasars, the brilliantly luminous cores of galaxies powered by supermassive black holes, consuming vast quantities of surrounding matter, blazed with a ferocity that has since diminished dramatically. The early universe was a more violent and more fertile place than the one we inhabit. Our own galaxy, the Milky Way, was assembling itself during this period, growing through mergers with smaller galaxies, building up its disk of stars, developing the spiral structure that gives it its characteristic shape. And approximately 4.6 billion years ago, in one of the Milky Way's spiral arms, a cloud of gas and dust, enriched over billions of years by the deaths of previous stellar generations, began to collapse. At its center, a new star ignited. We call it the Sun. Around it, the leftover material clumped and collided and swept into orbit, slowly organizing itself into the system of planets, moons, asteroids, and comets that we call home. The third planet from this new star was in what astronomers call the habitable zone, the range of distances at which liquid water can exist on a planetary surface. It was also the right size to hold an atmosphere, to maintain geological activity through the heat of its formation and the decay of radioactive elements in its interior, to recycle carbon through volcanic outgassing and weathering. It was, in hindsight, extraordinarily well suited for what was about to happen. Approximately 3.8 billion years ago, within a few hundred million years of the Earth's formation, which is a remarkably short time on geological scales, the chemistry of life began. We do not know exactly how. The origin of life is one of the deepest unsolved problems in science, and honest scientists acknowledge that we are still far from a complete understanding. What we know is that self-replicating molecules appeared in the early oceans, and that once they did, the process of evolution, of heritable variation and differential reproduction, began its slow, blind, magnificent work. For the first 2 billion years of life on Earth, all living things were single-celled, simple by modern standards, but chemically extraordinary, capable of photosynthesis, respiration, nitrogen fixation, and 1,000 other biochemical feats that still underlie all life today. Around 2.4 billion years ago, the Great Oxidation Event transformed Earth's atmosphere. Photosynthetic bacteria had been pumping oxygen into the air for hundreds of millions of years, and the oxygen finally began to accumulate, poisoning many existing life forms while opening the door to new ones capable of using oxygen's extraordinary chemical energy. The atmosphere we breathe today is, in the most literal sense, a biological creation, a waste product of ancient microbial metabolism that became the foundation of all complex animal life. Complex cells with nuclei, eukaryotes, appeared perhaps 1.8 billion years ago. Multicellular life began experimenting about 600 million years ago. And then, in one of the most dramatic episodes in the history of life, the Cambrian explosion, roughly 540 million years ago, produced an astonishing diversity of body plans in what appears, geologically speaking, to be a very short time. Eyes appeared for what may have been the first time. Predator-prey relationships drove an evolutionary arms race that accelerated the pace of adaptation. The ocean filled with animals of extraordinary variety, most of which would leave no descendants at all. Life moved onto land around 375 million years ago. Forests of vast scale appeared and drew down so much carbon dioxide that they may have triggered a mass extinction through global cooling. The first reptiles developed the amniotic egg, which freed vertebrate life from dependence on water for reproduction. The dinosaurs rose and dominated terrestrial ecosystems for 165 million years, longer than the entire span from their extinction to today. And then, 66 million years ago, a rock roughly 10 kilometers in diameter struck what is now the Yucatan Peninsula at a speed of perhaps 20 kilometers per second, releasing energy equivalent to billions of nuclear weapons simultaneously, triggering wildfires across continents and throwing enough debris into the stratosphere to block sunlight for years. The non-avian dinosaurs were gone within a few tens of thousands of years, but the small, warm-blooded, furry creatures that have been living in their shadow for 100 million years, hiding in burrows, foraging at night, staying out of sight, survived, and in the ecological void left by the dinosaurs' extinction, mammals diversified explosively. Within 10 million years, every major group of modern mammals had appeared. Within 30 million years, the ancestors of primates had taken to the trees. Within 65 million years, a lineage of upright walking apes was standing on the African savanna, looking at the sky with eyes capable of perceiving depth and color, with hands capable of making tools, with brains large and complex enough to ask what those lights in the darkness above them were. And here we are, standing at the end of that improbable chain, looking up at the same sky that was dark for the first 500 million years of the universe's existence, wondering. Now let us look forward, because understanding where we are in cosmic time is not just about appreciating the past, it is about grasping the full sweep of what the universe is and what it will become. And the future of the cosmos is something that most people have never seriously considered, because it operates on timescales so vast that our ordinary intuitions simply break down. The universe we currently inhabit is, by cosmic standards, young. The Stelliferous Era, the age of stars, began a few 100 million years after the Big Bang and will continue for approximately 100 trillion years. That is 10,000 times the current age of the universe. Our sun has been burning for 4.6 billion years and has another 5 billion or so to go. In the grand timeline of stellar life, we are in the early chapters, but the overall trend is already clear, and it points in one direction: decline. Star formation has been slowing since its peak 10 billion years ago. The universe is consuming its reserves of cold hydrogen gas, the raw material of stars, and not replenishing them fast enough. New stars are still forming and will continue to form for a very long time, but at a diminishing rate. The universe is slowly spending down its creative capital, like a fire that has burned through most of its fuel and is beginning, almost imperceptibly, to dim. Our own sun will follow the path of all stars. In about 5 billion years, it will exhaust the hydrogen fuel in its core and begin to expand into a red giant, swelling outward until it engulfs Mercury and Venus, and possibly Earth, scorching our planet's surface, boiling away the oceans, stripping the atmosphere. Life on Earth will have ended long before that, As the sun gradually brightens over the coming billions of years, and the planet's surface temperature rises beyond what biological systems can tolerate, in perhaps 1 billion years, the Earth's oceans will begin to evaporate. In perhaps 2 billion, the planet's surface will be uninhabitable by anything resembling life as we know it. The window for Earth, already remarkably long, will have closed. After its red giant phase, our sun will shed its outer layers in a beautiful, expanding shell of gas called a planetary nebula, and its core will remain as a white dwarf, a dense, hot remnant about the size of the Earth, no longer fusing hydrogen, slowly radiating away the heat of its formation over billions of years. Eventually, given enough time, it will cool to a black dwarf, a cold, dark, inert ball of crystallized carbon and oxygen drifting through space. But the universe is not yet old enough for any black dwarfs to exist. The cooling process takes longer than the current age of the cosmos. The longer-lived stars, the small, dim, miserly red dwarfs, will outlast our sun by enormous margins. A red dwarf with 1/10 the mass of our sun burns so slowly and so efficiently that it can live for 10 trillion years. These are the marathon runners of the stellar world, and they will be the last stars burning in the universe long after everything else has gone dark. In the very far future, the sky of whatever world exists near a dying red dwarf will be filled not with the brilliant, varied light of a youthful galaxy, but with a single dim, rust-colored sun and a darkness in all other directions where galaxies once glowed. The last star will burn alone, but even the last star will eventually die. And when it does, the universe will enter a new phase, the degenerate era, dominated not by living stars, but by their cold remnants. White dwarfs, slowly fading. Neutron stars, spinning in the dark, their pulses growing weaker over millions of years as they radiate away rotational energy. And black holes, those extraordinary regions of space-time where gravity has overwhelmed all other forces, where matter has been compressed beyond any point of return, where not even light can escape. Once it crosses the event horizon, black holes will come to dominate the degenerate era. As stars die and their remnants cool and dim, the black holes that formed from the most massive stellar deaths will persist and grow as they absorb stray matter and merge with other black holes over cosmic timescales. The supermassive black holes at the centers of galaxies, like the one at the center of our own Milky Way, 4 million times the mass of the Sun, will slowly accumulate mass for as long as there is anything to consume. And in a universe growing emptier and colder, they will become the dominant structures, the last great concentrations of mass and energy in an otherwise featureless expanse. But even black holes are not eternal. In 1974, the physicist Stephen Hawking made a prediction that shocked the scientific community. Black holes should slowly radiate energy through a quantum mechanical process at their event horizons. This Hawking radiation, as it came to be called, is so faint for large black holes as to be completely undetectable by any instrument we can currently imagine. The temperature of the radiation from a stellar mass black hole is less than 1/1000th of a degree above absolute zero, far colder than the current temperature of the cosmic microwave background. But given enough time, it is real, and it means that black holes are not immortal. They are slowly evaporating, losing mass at a rate that increases as they shrink, until in the final moments of their existence, They flash away in a burst of high-energy radiation. How long does this take? For a stellar mass black hole, something like 10 to the power of 67 years. A number so large that writing it out in full would require more digits than there are atoms in the observable universe. For the supermassive black holes at galactic centers, something like 10 to the power of 100 years. These numbers are so far beyond anything that corresponds to human experience that they are effectively meaningless to our intuitions. But they are finite. The black holes will evaporate. And when the last one does, when the most massive black hole in the universe finally radiates away its last quantum of mass energy, there will be nothing left. No matter, no structure, no concentration of anything. Just an unimaginably cold, thin, diffuse sea of photons and elementary particles at the maximum possible entropy, drifting apart at the speed of light, with no more interactions to come. Forever. This is what physicists call the heat death of the universe. Not a bang, not a crunch, not a dramatic ending of any kind. Just a slow, inexorable approach to a final state of perfect equilibrium in which nothing can happen because nothing has anywhere left to go. The universe ends not with violence, but with silence. Not with fire, but with cold. Not with an event, but with the absence of any possibility of event. And from that final state, from that ultimate silence, there is, as far as we know, no return. Now come back to tonight. Come back to this window, this sky, these stars. Do you see it differently? Because you should. Every star you can see with the naked eye is a temporary phenomenon in a universe that was dark before they existed and will be dark again after they are gone. Every galaxy visible through a telescope is a structure that did not exist for the first several 100 million years of cosmic history and will not exist in anything like its current form, trillions of years from now. The warm, bright, complex universe we inhabit is not the default state of things. It is an exception, a brief and precious exception. And we should go further, because there is one more dimension of our extraordinariness that is almost never discussed. The question of what future civilizations, if any exist, will be able to know about the universe compared to what we can know today. The universe is not just expanding, it is accelerating in its expansion. The mysterious force driving this acceleration, which we call dark energy, ensures that distant galaxies are receding from us at increasing speeds. There is a distance beyond which galaxies are moving away from us faster than the speed of light. Not because they are moving through space at that speed, but because the space between us and them is expanding fast enough to carry them beyond any possible communication. Their light will never reach us again. They are effectively gone, removed from our observable universe by the inexorable expansion of space itself. Right now, we can observe roughly 2 trillion galaxies in the observable universe. We can map the cosmic web, measure the cosmic microwave background, detect gravitational waves from merging black holes, study the large-scale structure of the cosmos in extraordinary detail. We have access to an enormous amount of cosmological evidence that allows us to reconstruct the history of the universe from its first fractions of a second to the present day, and to project forward with reasonable confidence about what will happen in the deep future. But this will not always be the case. In approximately 100 to 150 billion years, long after our sun has died, long after the Milky Way has merged with the Andromeda galaxy in a slow-motion collision that will unfold over billions of years. The accelerating expansion of the universe will have carried all galaxies beyond our local group over the cosmological horizon. Future astronomers, if any exist in the Milky Way Andromeda merger realm, will look out into space and see nothing. A vast, dark, empty void in every direction. The cosmic microwave background will have been redshifted to undetectable wavelengths. The evidence for the Big Bang will have faded beyond any possible observation. The cosmic web will be invisible. The existence of other galaxies will be unknown and unknowable. Those future astronomers, working from the evidence available to them, might reasonably conclude that the universe consists of a single island of stars, their own, surrounded by infinite, empty darkness. They will have no way of knowing about the Big Bang, no way of measuring the Hubble constant or detecting the expansion of the universe, no way of discovering dark energy, because there will be no distant galaxies to show the acceleration. The entire cosmological framework that we have built, one of the greatest intellectual achievements in human history, will be inaccessible to them, erased not by any failure of intelligence or curiosity, but simply by the geometry of an expanding universe that has carried the evidence beyond reach. We live at the only moment when the universe can be fully understood. Every year that passes, a little more evidence drifts beyond the horizon. We are, right now, at the peak of cosmic legibility. The cosmologist Lawrence Krauss and his colleague Robert Scherer wrote about this in a 2007 paper titled "The Return of a Static Universe and the End of Cosmology." Their conclusion was stark. Future scientists, no matter how intelligent, will be unable to deduce the true nature of the universe from the evidence available to them. They will be, in a profound sense, cosmologically blind, not because they lack the tools, but because the universe will have hidden its own history from them. The era of observational cosmology has a beginning and an end, and we are living in its golden age. That knowledge carries a responsibility. Everything we have learned about the Big Bang, about cosmic inflation, about dark matter and dark energy, about the large-scale structure of the universe, is knowledge that is available now and may become unavailable forever. We are not just the current generation of curious beings. We are potentially the only generation of beings for whom the full picture is accessible. Every observation, every measurement, every paper published in a cosmology journal is an act of preservation, saving knowledge that the universe itself is in the process of destroying by expanding it away. But let us not forget the human dimension of all of this, because the cosmic perspective, as humbling as it is, cuts in two directions. Yes, we are small. Yes, we are brief. Yes, the universe will continue for incomprehensibly longer than we have been here, and it operated for billions of years before we arrived, and it will operate for trillions of years after we are gone. All of that is true. None of it makes us insignificant. Consider what it takes for the universe to produce a mind. Start with hydrogen, the simplest possible atom, one proton and one electron. Give it 13.8 billion years. Watch it collapse into stars, burn, explode, scatter, recollect, burn again, in cycle after cycle of stellar birth and death. Watch the chemical complexity grow, one generation of stars at a time. from hydrogen and helium to the entire periodic table. Watch planets form around a new star, cool, develop liquid water, spawn chemistry that somehow crosses the threshold into life. Watch that life evolve for billions of years, growing more complex, more capable, more aware, until it produces an organism that can hold all of this history in its mind at once, that can look at the light arriving from a star 100 light years away and understand correctly that this light left its source before any living human was born, that it has been traveling through the vacuum of space for a century, and that the star it came from is a nuclear furnace, converting 4 million tons of hydrogen into energy every second. That is not a trivial achievement. That is the universe doing something it has almost certainly never done before. Or if it has, in other places, at other times, it has done it rarely enough that we have found no evidence of it after decades of searching. The emergence of understanding, of genuine comprehension, may be one of the rarest phenomena in the cosmos, rarer than the formation of planets, rarer than the existence of liquid water, rarer than life itself. And we have it, right now. In this moment that we are sharing, you, listening, and this voice, reaching across whatever distance separates us, we are two instances of the universe, understanding itself. Two temporary configurations of matter that arose from the same hydrogen that filled the cosmos after the Big Bang, that were assembled from elements forged in dying stars, that are sitting on a warm, rocky world at just the right distance from a middle-aged star, in the right era of cosmic history, with the right kind of nervous system, having the right kind of conversation about the nature of everything. This is, as far as we know, what the universe has been working toward for 13.8 billion years. There is a concept in physics called the anthropic principle, the observation that the universe we observe must be compatible with the existence of observers, because if it weren't, we wouldn't be here to observe it. In its weak form, this is almost tautological. Of course, we find ourselves in a universe that permits our existence, but in its stronger forms, it raises genuinely profound questions. Why are the fundamental constants of nature so precisely tuned for complexity? The strength of gravity, the charge of the electron, the mass of the proton, the cosmological constant that governs the expansion of the universe. All of these values sit in extraordinarily narrow ranges that allow for the existence of stars, planets, chemistry, and life. Change any of them by even a small amount, and the universe either collapses back on itself before stars can form, or expands so fast that matter never clumps into anything interesting, or burns through its hydrogen so quickly that there is no time for planets and evolution, or produces atoms too simple for chemistry. We do not know why the constants have the values they have. We do not know whether they could have been different, or whether they are fixed by some deeper mathematical necessity we have yet to discover, or whether we live in one of an enormous number of universes, a multiverse, each with different constants, and we are simply in one of the rare ones where the values permit our existence. These are open questions at the frontier of physics and cosmology, and honest scientists acknowledge that we are nowhere near resolving them. What we can say is that the universe appears, at minimum, to permit complexity. And in permitting complexity, it has, at least once, and possibly many times in ways we cannot yet detect, produced beings capable of asking why. That question, why is there something rather than nothing, is one of the oldest in philosophy, and it remains unanswered. But the fact that it can be asked at all, the fact that matter has arranged itself into configurations that can formulate questions and seek answers, is itself one of the most remarkable features of the universe. It is easy to imagine a cosmos that permitted no such thing, that produced only hydrogen gas, or only radiation, or complex stars and planets, but nothing that ever developed the capacity for awareness. Our universe did not stop at stars. It went further, and we are what it produced when it went further. On clear nights, far from city lights, you can see the Milky Way, a faint band of light arching across the sky, the combined glow of hundreds of billions of stars, too distant to see individually. That band of light is our galaxy, seen from the inside. Every star in it is a sun. Many of those suns have planets. Some of those planets are in habitable zones. Some of those may have liquid water. Some of those may have life. We do not know. We have been searching with increasingly sophisticated tools for any sign of biology or technology beyond our own planet. And so far, silence. The absence of detected alien civilizations is itself one of the most profound puzzles in science. What the physicist Enrico Fermi famously condensed into a single question, where is everybody? The universe is 13.8 billion years old. It has had time to produce technological civilizations billions of years before our own. Even at speeds far below the speed of light, a civilization motivated to explore could theoretically spread across the entire galaxy in tens of millions of years. If such civilizations existed in abundance, we would expect some evidence of their presence. We find none. Perhaps they are rare. Perhaps they are distant. Perhaps there are barriers to survival, what theorists call the Great Filter, that most potential civilizations do not survive. Perhaps the emergence of intelligence is so improbable that we are the only example in our observable universe. We do not know. And the not knowing sits in the back of every serious conversation about the cosmos, like a weight that never quite goes away. But consider what it would mean if we are alone, or nearly so. If the emergence of understanding in the universe is a rare event, perhaps unique to us in all the vast expanse of space and time we can observe, then everything changes. The universe is not full of minds contemplating itself from countless vantage points. It has one, or very few. And those few are precious beyond any calculation, not because of what they have built or discovered or created, though those things are real, but because they are the universe's only way of knowing that it exists at all. Without observers, the universe happens but is never witnessed. We are the witness. There is a kind of vertigo that comes from fully absorbing this. It is not a comfortable feeling. The scale of the cosmos, the brevity of our moment, the uncertainty about our uniqueness, but it is an honest feeling. And there is something on the other side of that vertigo that functions like awe, or like gratitude, or like the particular clarity that comes from understanding where you actually are, rather than where you imagined you were. You are on a rocky world, orbiting a yellow star, in the outer regions of a spiral galaxy, in a universe that has been expanding and evolving for 13.8 billion years. You are made of atoms that were forged in the hearts of stars that died before the sun was born. You have evolved over billions of years from the first self-replicating molecules in the early oceans of this planet. You exist during the Stelliferous Era, the bright chapter of cosmic history when stars are still burning and the universe is still warm enough for complexity and life. You live at the only moment when the full architecture of the cosmos is observable and understandable, and you are capable, right now, of holding all of this in your mind at once. That is an extraordinary position to be in, and it is temporary in every possible sense of that word. Temporary for you as an individual, temporary for our civilization, temporary for our species, temporary for our planet, temporary for our star, and on the longest timescales, temporary for the universe itself, which will eventually arrive at a state of cold, featureless equilibrium from which nothing new can emerge. But temporary does not mean worthless. In fact, it may be the case, and I want you to sit with this thought, that the temporary nature of beauty and complexity and understanding is precisely what gives them their value. The stars are beautiful, partly because they will not burn forever. This moment is precious, partly because it will not last. The universe has gone to enormous trouble. 13.8 billion years of stellar evolution and chemistry and biology and neural complexity to produce something capable of noticing that it exists. The least we can do is notice. Look up tonight, if you can. Find a place away from the lights. Lie down on the ground and give the sky your full attention. Let your eyes adjust until the faint smudge of the Milky Way resolves itself from the general darkness. Find a galaxy. The Andromeda galaxy is visible to the naked eye on a clear night. A faint, elongated glow in the constellation bearing its name. And consider that the light arriving at your eyes from that galaxy left its source roughly 2.5 million years ago, when our own ancestors were small-brained hominids on the African savanna, when the ice ages were just beginning, when no member of our species had yet drawn breath. That light has been traveling for 2.5 million years through the emptiness of intergalactic space, and it ends its journey on your retina in this moment, tonight. Consider that Andromeda contains roughly 1 trillion stars, 5 times as many as the Milky Way. Consider that almost every one of those stars almost certainly has planets. Consider that the observable universe contains approximately 2 trillion such galaxies, each with hundreds of billions of stars. The numbers are so large that they stop meaning anything specific to our intuitions. They become simply enormous, a magnitude beyond our natural grasp. But they are real. The universe is genuinely that large, genuinely that old, genuinely that populated with the raw material for complexity. And out of all of it, out of 2 trillion galaxies and their hundreds of billions of stars each, we know of exactly one place where something looked up and understood what it was seeing. One small, rocky, warm, wet world. One lineage of organisms that develop large enough brains and complex enough social structures to accumulate knowledge across generations. One species that built telescopes and mathematics and the scientific method that learned to read the light from distant stars and extract from it their composition and temperature and motion, that reconstructed the first movements of the earth from a faint light filling the entire sky. that deduced the existence of black holes decades before any were observed, that detected ripples in space-time from collisions that happened billions of years ago and billions of light years away. We did all of that in the last few centuries on a single planet, in the bright, brief window of a fortunate era. The universe is 13.8 billion years old, and it will exist for trillions of years more. The Stelliferous Era, our era, the age of stars, will continue for another 100 trillion years. In the context of that timeline, our entire civilization, from the first stone tools to the present day, is a duration so short it would not register on any cosmic scale. And yet, in that unmeasurable sliver of time, this improbable arrangement of matter called humanity has managed to understand, at least in outline, the full arc of the universe, from the quantum fluctuations of the Big Bang to the eventual evaporation of the last black hole. We have looked at the beginning and the end of all things and made sense of them. That is enough, more than enough. That may be the most remarkable thing that has ever happened in this universe, or in any universe. And it is happening right now, tonight, in this moment that will not come again. The stars are burning, the galaxies are drifting, the universe is expanding, slowly dimming, moving toward its eventual silence. And somewhere, on a small rocky world, in a quiet spiral arm of an unremarkable galaxy, a creature made of ancient stardust is looking up and wondering and understanding and feeling the full strange weight of being here at all. That creature is you. This moment is now.